Alright, let's look at the vector product or cross product of vectors. Alright, let's say you have vector A and vector B, just like before, and vector A cross vector B is defined to be, right? I'm going to use the determinant notation. Here is the vector I and vector J and vector K. Right? And note that the vector I is simply 1, 0, 0, and the vector J is just 0, 1, 0, and the vector K is 0, 0, 1. Right? Then, so first you write down the component of vector A. So I'm going to put A1, A2, and A3. And then B1, B2, and B3. Right? Using this notation, actually, let's go dive right into an example. Right? How do you compute this? Right? So let's try to find a vector perpendicular to both these two vectors, I minus 3j plus 2k and 5I minus j minus 4k. And one of the property of vector product is that vector product is going to be always a vector which is perpendicular to both of these vectors. So it's perpendicular to A and perpendicular to B. Alright, so if you're looking for a vector perpendicular to two vectors, all you really have to do is take the vector product of those two vectors. Alright, so let's do that. So what we're looking for would be determinant. Alright, then I put the vector I, vector j, vector k. Alright, and the first vector is 1, -3, and 2. And the second one is 5, -1, -4. Right? So this is going to be, right, so I'm going to expand it along first row. Right? So this is going to be vector I times the cofactor, let's see, cofactor of this matrix. So you have -3, -2, -1, -4. Right? Then since it's a first row, first column, so -1 to the 1 plus 1, so it's a +1. Right? Then you have let's see, j, so plus j times, and a cofactor would be actually negative, so it's a negative. Right? Then you have so you erase this guy and that guy, so 1, 2, 5, -4. Right? So that will be the cofactor of 1, 2, C1, 2. And then C13 would be, so it's going to be k times, right? Then you have 1, -3, 5, -1, right? So to get is going to be, right? So this is -3 times -4 would be 12, and minus, let's see, negative. Right, so 12 minus 2, actually I messed it up somewhere. Yeah, I think, okay, I messed up the sign, sorry. Here. Alright, so it's going to be 12 minus -2, so it's going to be 14. So 14i. And then this is going to be negative, let's see, 1 times -4 is -4. Minus 10, so -14 with a negative sign, so it's a positive 14 j, right? And the plus, right, it's -1 minus negative 15, so another 14. Okay, right, which is the same thing as I'm gonna pull out 14, so 14, then it's a 1 comma 1 comma 1, right? So if you're looking for just a vector, and you can use the whole thing, but a vector that's perpendicular to both would be 1 comma 1 comma 1, right? Right, so that's an example. Right, so that's how you compute the vector product. I just rescaled it because it's multiplied by 14. All right, and another thing we would like to talk about would be the norm, or the magnitude of the vector product. So so we know that let's see, vector, if you take the magnitude of the vector product, is always going to be magnitude of A times magnitude of B times sine of theta and angle theta, so that's the angle between vector A and vector B. And geometrically, if you look at the vector A and the vector B, right, so this is going to give you the area area of the parallelogram created by those two vectors. So we're looking at this region right here, so parallelogram here, right? Because magnitude of A, so this guy right here is going to give you the base, right? And the vector V, magnitude of vector B times sine of theta. So theta is the angle here. Oops. Right. So this is going to be the angle theta, and this is the length here. This is the magnitude of B times sine of theta, which gives you the height of the parallelogram. So this is going to give you the height. So therefore, this is equal to the area of the parallelogram. Right. Then, as I mentioned, that the vector product is always perpendicular to vector A and vector B, and the direction, you can use the right-hand rule, and you probably have heard of it in physics class. So if you have a vector A and a vector B this way, so you have a vector A and a vector B, then what you can do is you can put your hands, put your fingers curling from A to B. So you have a hand curling this way, right? Then you have to use the right hand anyway. So then the direction of the thumb is going to be the direction of the cross product. So here, in this case, orientation, this is going to be the direction of vector A cross vector B. All right. If you have a vector, say vector A is going this way, say vector B is say going that way. So here's a vector A, and here's a vector B. Right. Then if you curl the vector A toward vector B, your hand is going to look like this. Right? So right hand rule, it actually vector points this way. Right? So this is A cross B. Right? So again, the magnitude of the cross product represents the area of the parallelogram formed by those two vectors, and the direction of the vector product is always, you can follow the right hand rule. If you curl it from A to B, or the first one to the second one, then the direction of the thumb is going to be the direction of the vector product. So this is called the right hand rule. All right, that's it. I hope that this was clear.